All right, hello there. So we probably started these notes in class, so feel free to skip around and everything. I'm just going to do all of the notes, and you can start wherever you need to. So here we go. So I'm going to start back down here. Now, what's important to notice here is that a lot of the things in this in linear algebra, it's going to be like a language, and so right here where it says it is a language, that is like so true, because there's going to be all these terms and definitions and things that you know that are called something else now. So maybe have a highlighter ready, because some of these notes I'm just going to be highlighting so that we can, like, I don't know, it's just like a term for something you already know that happens. So anyway, just like this first one, a linear equation. So a linear equation, you know, like we've been doing linear equations like y equals 4x plus 5. If it's in standard form, you know, it could be like 3x plus 2y equals 7, things like that. And so, you know, linear algebra, a lot of times, you know, you're going to run out of letters. So like there's only 26 letters in the alphabet. And so instead of using letters, they use x1, x2, and so forth on to xn. And so don't be confused by that. It's just how it goes, because like you saw in the video, there's systems of equations that have hundreds of variables to them. All right. So first of all, to be a linear equation, none of your variables can be, nothing tricky can be done with them. You can be multiplied together, can't have square roots on them, can't have a fraction with a variable on the bottom. So like letter A is fine, because this square root right here, the square root of 2 is a coefficient. That's perfectly fine. But what's not good is this right here. You can't multiply two variables. You can't have a variable to a negative exponent, because that means the variable's on the bottom, you know, the denominator. Everything else in letter D is fine. You got some nasty coefficients, 2 to the 1/3, pi, but that's fine. All right, so it's not that these aren't equations, B and C, but they're just not linear equations, right? And then remember, with linear equations, three things can happen to you, right? You can have no solution, two lines never cross or parallel, two lines meet one time, or maybe the lines are right on top of each other. Remember, that's infinite solution. So these words that you saw like way back in Algebra 1, you're going to see them again, and they have also different words that go with those things. All right, so you know, back in Algebra 1, when you were doing these, like when you saw right here, oh, sorry about that, never mind. So yeah, I think I'm done with this page. I thought we was going to solve that example, but that's on the next page, I was remembering. All right. So now you're going to have to think in 3D a little bit, coming down with these planes right here. But first, there's a definition of what's deemed consistent and inconsistent. So something that's consistent. Consistent means you have an answer. There is some answer to be found. There might be one solution or infinite solutions, but there is an answer. So if a system is consistent, that means there is some answer to find. Whereas the term inconsistent means there is no solution to find. All right. All right, so down here, when you have three equations and three variables, then it turns into 3D, right? And so these are just pictures of three different, each of these pictures has three planes in it, even though sometimes you can only see two. If you can only see two, that means that that means that some of them are together, like on top of each other, or maybe you can only see one because they're all three on top of each other. And so how many solutions would the system have? So letter A, these three planes are all parallel to each other, so they don't touch each other at all. So no solutions, right? Letter B, so there is a solution to these two planes right here, a line, and then these two right there, but all three of them don't have any solutions together. So all three together, no solutions. Letter C, same thing. These two meet right here, these two meet right there, these two meet down here at that line, but all three together, they don't meet. Letter D, they're all on top of each other. They're the same plane, right? So this is infinite solutions. Letter E, they're all meeting at this line right here. So while it's one line where they meet at, and you could find that line, you know, they meet at infinitely many points though. So that's also infinite solutions. These three planes in letter F, they're set up kind of perpendicular there, and so they meet at one place, so one solution. Letter G, so two of the planes must be together, and then the third one's just separate. But again, all three of them together, no meeting places. And letter H, infinite solutions. It must be that two of them are like together, and then here's the third one down here, and they're meeting at this line, which is the same reason as letter E, infinite solutions. All right, equivalent systems are basically two linear systems with the same solution set. And so they're called equivalent because when you do your row operations and all your reductions and all that, what's going to happen is they're going to be the same at some point, and so they're equivalent. All right, so some quick little things here. You can solve with linear combinations. You know this from Algebra 1 and also from today. You add these together because you see these are going to cancel. So like, oh, x2 equals 2, and then you go on from there and plug it into the other one and get x1 equals 3. So you guys know how to do that already. Okay, now remember what we did in class today is when we were doing our row operations and we did augmented matrices, we came out with these three things. We did reduced row echelon form. We came out with matrices that look like this. And then you had three numbers right here, and those were basically your three answers, right? When we came out with a matrix like this, and then we had this, and we had 0 here. Remember, this was infinite solutions. Yes, sorry about that. So infinite solutions here, because later you'll learn we have something called a free variable. And that would be this one right here, but you'll learn that later. And then what happened also is when we had this one right here, if this was a 1 but that was a 0, so what that meant, that was no solutions, remember? So we're going to be talking about these things in this next example here. There's 3 types of scenarios, so just remember those things and what we did there. All right, so this is going to be a generic scenario here because we have this k and this h right here. So let's see, I'm going to multiply the top by -4 to get rid of the x1s. So I have -4x1 plus, minus 12x2 equals -4k. Then I got 4x1 plus hx2 equals 8. And we're doing this because I want to see what h and k have to be for there to be no solution, unique solution, and infinite solutions. All right, so if I add these together, this is gone. I would get h minus 12 with x2. So I'm going to put h minus 12 with x2. And this, if I put it nicely, I'll have 8 minus 4k. Okay, all right. So what we're going to have right here is our 3 different scenarios, right? So the first scenario is that there is no solution. Our second scenario is that there is one solution. And our third scenario down here that they're asking me about is that there is infinite solutions. All right, so remember what has to happen here is there's infinite solutions. That means that both of these things have to be 0. Okay, kind of like what we saw with the 3 by 3, right? So infinite solutions, both of those things would have to be 0 because they basically go away, right? So h minus 12 has to be 0 and 8 minus 4k has to be 0. So basically this tells us h would have to be 12 and k would have to be 2. If that happens, then we are going to have infinite solutions because that means that the second line is just a repeat of the first, that they all canceled itself out, okay? If there's going to be one solution, 8 minus 4k can equal anything. I don't care what it is, but h minus 12 can't be 0. So h minus 12 cannot be 0 because it would have to be some kind of number that I would divide into 8 minus 4k, and I would get an answer for x2, right? So h cannot be 12, right, if there's going to be one solution. And if there's going to be no solution at all, what would have to happen is that one of these items would have to be 0 and the other one cannot be 0. All right, so that would mean that h minus 12 would have to be 0. It would have to go away, and 8 minus 4k wouldn't go to 0. So 8 minus 4k would not be 0. So h would have to be 12 and k could not be 2. So that would be, sorry I did those kind of backwards, but it just seemed more obvious to me to do it that way. All right, So, some more definitions down here. A rectangular array is called a matrix, all right? And you know that matrices are rows and columns. An M by N matrix would be a certain number of rows and columns. You'll see this M by N in many places. I don't know why they use M and N, but there must be a reason. Anyway, a coefficient matrix is when you steal all the coefficients, 1, -2, -1, 3, and you put them in a matrix. Okay, and then you have what is called an augmented matrix. Now I like to go ahead and when I'm writing these things, I like to draw a little line right here just to make sure I remember that it's augmented and so forth, just so I know that those are my answer pieces right there. Okay, so you saw today in class you can do elementary row operations. You can multiply any row by a number, constant, and add and subtract with another row to replace one of the rows and so forth. So I'm going to do these next two examples, but you can skip over these. I mean, we did this in class. But anyway, if that messed you up in class today, then I don't know, or if you didn't quite get it, then you can watch this. If not, then just skip it. All right, so anyway, there's a typo on here. This is supposed to be a negative sign. Okay. All right, and let's go. So I'm going to write this as an augmented matrix. 1, -2, 3, and 9, and -1, 3, 0, and -4, 2, 5, -5, that is, 5, and 17. Remember, we have to write down what we're doing. So I know that there's a 0 right here, right there, but I feel like it's going to be hard to make this 3 or this 5 disappear. So I'm going to go ahead and go with the easy thing. I'm going to add these together so this goes away. Then I'm going to multiply -2 times 1 and add it with this guy to make that go away. So I think I can get my x's to go away pretty easily. So remember, we have to write down what we're doing. So my new row 2 is going to be row 1 plus row 2. That's going to be my new row 2. And my new row 3 is going to be -2 times row 1 plus row 3. That's going to be my new row 3. So row 1 is still the same. So when I do that, I get 1 plus 1. So -1 plus -1 is 0. -2 plus 3 is 1. I get a 3 here, and I get a 5 there. -2 times the top row of 1 is -2. -2 plus 2 is 0. -2 times this -2 makes me a 4. So 4 plus -5 makes me a -1. And I also get -6 plus 5, so I get -1 again, and then I get -18 plus 17, so I get -1 again. And so now I easily notice that I can get rid of this right here if I would add it with that. So my new row 3 is going to be row 2 plus row 3. All right, so I'm going to write that down here. I'm kind of out of space. So 1, -2, 3. So it's a lot of writing for these things. All right, so 0, this would add up to 0, this would make 2, and this would make 4. So I can easily tell now that x3 is equal to 2, which allows me to find x2 if I put it in here. So I have x2 plus 3 times 2 equals 5. So that means that x2 is equal to -1. And then you can put it back in any equation you want, but I'm going to put it in the top equation. I have x1 minus 2 times x2, which is -1, plus 3 times x3, so that's 2 equals 9. So let's see, that's x1 plus 2 plus 6 equals 9, so x1 must equal 1. So I get my solution, 1, -1, 2. Okay? All right, so why don't we, so we'll go ahead and do this one too. All right, let's see. 1, 1, 2. Again, skip this, please. It might be a little bit redundant from what we did in class. 2, 4, -3, 3, 6, -5. All right, so let's see. I'm going to do -2 times row 1, and I'm going to add it to row 2. Then I'm going to do -3 times row 1 and add it to row 3. That's going to be my new rows. So 1, 1, 2, and 9. All right, so this makes 0. That was my plan. The -2 times the 1 up there. This gets me a 2 here. Then I get -2 times 2 for the third column, so it's 4. Sorry, that's -4 plus -3, so -7. Then I get -18 plus 1, so I get -17. All right, this one goes away. Negative 3 plus 6 is positive 3. Let's see. Negative 6 plus negative 5 is negative 11. And then I get negative 27. Oh, so this has turned into a bit of a nightmare. So let's see. I'm going to do negative 3 times row 2. And then I'm going to do 2 times row 3. Okay, so 1, 1, 2, 9. This gets me 0. Let's see, negative 6, 21. 3 times 17 is 51. And down below I get 0, 6, and let's see, I get negative 22. And then 54. All right. So I don't really care if you keep this in matrix form, but obviously I can see these two right here. If I add them, those are going to go away. This is going to get me negative 1 x3, and then over here, this is going to get me negative 3. So I can tell that x3 is 3. Our goal is to solve these. It doesn't really matter if you keep your format up. But anyway, x3 is 3, and so if you go on and plug this in and solve the rest, you would get the answer of 1, 2, 3. Okay. All right. So moving on here. So this is the system that we solved earlier. What, 9, negative 4, 17. That was this one right here. That was this one. Is it consistent, the question? And remember, this is supposed to be a negative. You would have to say, yes, it is consistent. All right. Now, in this next one right here, I'm going to show you what you would get on the calculator, or what you would get as you're doing your calculations. You would get, if you started to work this problem, you would get 1, negative 2, 3, and negative 1. So that I put the first row right there. And then if you worked it out a little bit, you get 0, negative 3, positive 3, negative 6, and 8. Then you get 0, 3, negative 6, and 5. And so when you come to that realization of what's happening here, you would see, oh, wait a minute, these are the same. They would cancel if I subtracted or, added the opposite, but these would not. This is an inconsistency. So these are inconsistent. This one is no solution. So is it consistent? No, it is not. All right, and then the last little bit right here, for what values of h will this thing be consistent? So I want it to have a solution. So let's see. Let's multiply this guy. Let's just put it in matrix form first. 3, negative 9, 4, negative 2, 6, and h. All right. So I'm going to do negative 2 times row 1, and I'm going to add it to 3 times row 2. That's going to be my new row 2. Okay, so 3, negative 9, and 4 is going to stay. So negative 2 times this makes negative 6, and 3 times that makes negative 6, so those go away. Then I have negative 2 times this, so it's 18, plus oh, I didn't need that negative, did I? Sorry about that. So don't need this negative right here. All right. Let's see. So that would be, if I'm doing the second column, this would be negative 18 plus 18. So that'd be another 0. And then here, this would be 2 times 4, so 8 plus 3 times h. So 8 plus 3h. All right. So look what happened here. If I want it to be consistent, then this cannot equal some number. This has to be 0 also. So that means that 8 plus 3h has to also equal 0. So h has to equal negative 8/3. Now, the only thing it can be is infinite solutions if it's going to be consistent, but that's consistent. So there's my answer. Okay. All right, that's it.